We are going to start with a quick review of series and parallel circuits. Then we're going to do a bit of an activity where you guys are going to build me some series and parallel circuits. You're going to solve them, then you're going to have your friends solve them. You're going to give them to me for points, and if they're really good, I'm going to put them on the quiz or exam. We do have a quiz on Friday. It will be on the stuff up through today. Today we are also going to, after that, start talking about something called Kirchhoff's rules. They give you more tools for solving more difficult problems. The Kirchhoff's rules problems won't be on the quiz on Friday, but they will be on the exam eventually when we have an exam on this stuff. So they're tough. It's tough to put a Kirchhoff's rule problem on a quiz because they take a long time to do. There's a lot of algebra involved, but you're able to solve more difficult things. And real life is more difficult in general, so you get to solve more authentic, more real life types of problems. Does that make sense to you? Okay, so like being totally forthright and upfront, Kirchhoff's laws problems are tricky. That being said, I'm going to give you all the tools you need to solve them. Remember the deal I made at the very beginning. I said I make it as easy as I can. Some of it's not easy. It's just not. But I'll make it as easy as I can, and then you do the rest. Sound good? Okay, make sure you have all the tools. So that's what today's schedule is. So let's start. Review. If you have a single resistor, it has a certain amount of resistance. If I attach a voltage across it, if there's a voltage difference from point A to point B, from one side to the other by attaching a battery, I can figure out how much current goes through that using a relationship called Ohm's law. Ohm's law is commonly written V equals I multiplied by R. You could also write it I equals V divided by R. You could also write it as R equals V divided by I. All three of those are the same thing. It's a handy tool to have for ohmic resistors. There is such thing as a non-ohmic resistor. We aren't going to deal with them in this class, but you may have talked about them in lab. I think he skipped that part, but did he talk with the light bulb? Okay. With my lab, I skipped it. I don't like that part. It's just, it doesn't fit the format of the new software very well, and it's annoying. So I didn't know if he did it or not, but it's kind of neat watching the light bulb oscillate like that, though. I thought that was really cool. So that's something that's non-ohmic, doesn't follow Ohm's law because of the temperature difference, which we also talked about last time. Temperature dependence of resistance. All the stuff we're going to deal with in this class, though, is ohmic. It's going to follow Ohm's law. That's Ohm's law. It gets a little bit tricky when you have multiple resistors. You can have them in series. Where I have R1 and R2, and there's just a row. Just a straight line path. There's only one path. There are no junctions in it. What can you tell me about a series of resistors? You should be able to tell me a lot.
You can add them up.
You can add them up. Why would you do that? What does that tell you? What does adding them up give you? The overall resistance. The equivalent resistance is the term we like to use. When we're talking about the overall resistance, we talk about the equivalent resistance, which is literally, if I took those two out, I can replace them with some hypothetical amount of resistance that wouldn't change a thing. It would be exactly the same. It is the equivalent of these two. So R for the series, or R12. Sometimes you see it R sub S. Sometimes you see it as R sub 1, 2. Those mean the same thing. It's the equivalent for this set. What do you prefer? RS? Okay. R for the series equals R1 plus R2. Sometimes when I'm doing it in the problem, I like to label them as R12 just so I keep track of what series it is. But whatever works for you, they mean the same thing. What else can you tell me about a series? One other important piece of information. Luke, you got something for me? Where's the confidence?
Is the current the inverse of the
Nope. The current is the same through the whole thing. You're on the right track, though. You knew it was current. For series, current is the thing. If there's only one path, it should make sense that there's nowhere for it to branch, there's nowhere for it to split, so there's nowhere for it to change. So the current has to be the same through the entire series. So if I know the current into that series, I also know the current through 1 and the current through 2. So the current through the series is going to equal the current through 1, which equals the current through 2. So if I know what battery or what voltage is attached to this, and I find the equivalent resistance using this first part, I can find the current through that series. V equals IR, I is V divided by R. If I know V and I know R, I can find I. If I can find I through the series, I'll know I through 1 and I through 2. Because it has to be the same. Whatever is coming into that series is what goes through 1, it's also what goes through 2, and it's what comes out of the series on the other side, because there's nowhere for it to split. The voltages, V1 and V2, how would we get those? I know I now, and I know R from the given information. How would I find V? Yep. V equals I times R. So V1 is I1 R1, and V2 equals I2 R2. Not too bad. What if I put them in parallel with each other? What can you tell me about this? Emily, also make sure that the video last week, the screen wasn't showing up on the video. It was just a washed out white. So make sure that's not wrong. Okay, that's good news. The voltage has to be the same. Why? Because there is a junction. There's a split. And it's coming from this spot and going back to that spot where it comes back together. So whatever the difference is, if I'm going from one spot and getting to another spot both ways, then the change is going to be the same both ways. So V1 is going to equal V2, and it's also going to equal V across the parallel set. So V across the parallel set equals V1 equals V2. What else can you tell me?
The resistance is 1 over.
The overall resistance is going to go down. We're giving more paths for current to go through, so more current is going to get through, which means that the overall resistance is reduced. So 1 over the resistance for the parallel set is going to equal 1 over R1 plus 1 over R2. All right, we can find the equivalent resistance, we can find the voltages. What would we do to find the currents? All right, if you know V and you know R, you can find I, V equals IR, I equals V over R. So I1 is going to equal V1 divided by R1. I2 equals V2 over R2. Let's say R1 is much bigger than R2. R1 is the larger of the two resistances. Where is most of the current going to go? Path of least resistance, right? Literally, the least resistance is going to get more current because it's easier for the current to go that way. There's less resistance to it. Yeah. Awesome. So this is all old stuff. Not old, like we just learned it last week, but this is last week's stuff. At the end of that, we did combination. So we did one of each. We did a series, we did a parallel, and then we did a combination of series and parallel and put it all together and tried to figure it out from that. That's what I'm going to have you do. So what I'd like you to do is take out a piece of notebook paper, if you've got it, if you don't, borrow one from somebody who does. Just a blank piece of notebook paper, and you're going to draw a resistor.
Can we draw an iPad?
No, because we're going to share it and you're going to turn it into me.
Then you need a full piece?
It could be a half piece if you want, especially if you're going to share it with people. But you need a piece of blank paper.
You're the best, Grace.
It's true. It's true. I said you're going to draw a resistor. You're actually going to draw a set of resistors, is what I meant to say. I got to say all the words, or else the sentence doesn't make sense. your set of resistors, your circuit you're going to make. So listen up, because I'm going to give you the rules here. Your set of resistors, your circuit, is going to have one battery and at least 4 resistors in it. I don't care what combination you put them in. They could be in any organizational scheme you come up with. It's up to you. But you can do whatever you want. Number one, you have to be able to solve it, because you're about to. You're going to draw it and then solve it on the back of your paper. You're going to draw it on the front, solve it on the back. Then you're going to hand it to a friend or an enemy or just somebody you don't know very well. A frenemy, I don't care. You're going to hand it to somebody else in this room who's not me, and that person is going to solve it on the front as well, and then they can check their answer on the back. Then you're going to hand it to me at the end in about 15, 20 minutes, and I'm going to look at them all, give you some points, and if it's really good, I'm going to put it on the test at the end of the, or at the quiz at the end of the week. Sound like a good plan?
Yes, like a plan.
All right, so put real numbers in it, because you guys hate it when I don't do real numbers. At least 4 resistors and a battery. I'm going to give you 10 minutes to draw and start solving. Hopefully you'll get it done, but if you don't, that's okay. Up to 15 minutes, then we're going to hand it to somebody else. They're going to get 5 to 10 minutes to solve it, and then we're going to move on to the next thing. More complicated means it'll take a little longer, but it's better practice. Simpler means it's super easy, so it's not as good a practice, but it'll be easier for you and your partner. But that's fine, it's still fairly new. Emily got me some markers. Why don't we do a couple together? That way we don't get quite as much practice as I would have liked, but we still get good practice, and I know you're doing it right if we do it together. Sound good? Okay.
Still get the points.
Well, we'll see.
Oh, come on, please.
You guys want it both ways. Who thinks they've got a really, really good?
I think
it looks great. You want to put it up on the board and I'll help you solve it?
Oh, perfect. Can we do mine?
We're doing them one at a time. We'll see how much time we got. I still have some other stuff to talk about. It's a good one. There's nothing wrong with that one.
It's confusing.
If it has 4 resistors in it, it's a good one.
It does, and 1 battery.
Grace,
Yeah.
she went overdrive. She put 6 resistors in hers.
Oh my god. Please don't put this one. Yeah, this one does not need to be like this. Well, we saw this. Maybe it can be other.
End of the day, it doesn't matter how many are in there. You have a certain set of tools that you can use to solve the problems. The process is never exactly the same, but how I address these problems is always the same. I look at them, I try to take the smallest bites, I get the equivalent resistance. Sure it does.
Sometimes.
See, Grace doesn't mess around.
No.
She's like, if I'm going to practice,
Terrible drawing, but.
if we're going to practice hard. We want to get real good at what we're doing.
Oh, sorry.
That's all
I
right.
was trying to save time.
You did great. Thank you very much. This is intense, but what I see immediately right off the bat is that there are 3 bites I can take to simplify it. I see there's an initial parallel set right here. I see there's a series here in the middle, and I see that there's another parallel set over there. And any one of those is fairly simple to deal with. I can deal with each of those right away. Probably the easiest to deal with is the series, because it's just added up. So the 9-volt battery carries over. We get up to the top, and I have R12. I'll move. I gotta draw it. It's okay, it's all right. It's all good. I have R34. And then I've got R56. And I can figure out all of those things because I know how to deal with series and parallel. I think the easiest one is R34. R34 is equal to R3 plus R4, which is equal to 7 ohms. Yes.
Read off all the resistance.
Do you want to just move closer because there's a lot of them? I don't have a calculator on me, but I bet with you guys with your calculators, you can figure the rest of them out. R12 is going to be 1 over 3 plus 1 over 2, and then 1 over that answer. 1 over 3 is the same as 1/3, which is the same as 2/6. And then 1 over 2 is the same as 1/2, which is 3/6. So we get 5/6. What's 6 divided by 5? 1.2. So R12 is, you said 1.2 ohms? And that makes sense. It's smaller than the smallest one. And then over there we've got R5 and R6, which is 5 and 6. 1.5. Because it's going to be 3/6 plus 1/6, which is 4/6, 6 over. All right. Now, what do we have? We've got a battery attached to a series of resistors. That's actually not that bad at all. That's fairly straightforward. I know how to deal with this. I can deal with it by just adding them up. I've got my 9-volt battery. I've got my R total is equal to 1.2 plus 7 plus 1.5. That's 2.7, 9.7 ohms. That's what Cassie told me, right? You're just too fast for me. I can't write that fast. Now I know the overall voltage and I know the overall resistance. I can figure out the output current of the battery. I can figure out how much current the battery spits out. How do I do that? V equals I times R. I is V divided by R. I equals V divided by R. V is 9. R is 9.7. It's going to be a little bit less than 1. A little bit less than 1 amp spit out. You scored a touchdown and you spiked the football.
Yep.
Okay, so that's how much current leaves the battery and goes around the circuit. That's how much current leaves the battery and goes around the circuit. All of that current is going to go through all of these. How do I know? Because it's a series. And that's one of our rules for a series of resistors. Now, that first one, 1, 2, is actually a parallel set. So I can't deal with that one yet. The last one, R56, also a parallel set. Because that current is going to come in and it's going to split. So I don't know how much is going to go to each branch, at least not yet. And I don't know how much is going to go to each branch of this, at least not yet. But I do know that whatever is going through a series is going through the stuff in that series, and the stuff in this resistor, which is in that series, 3,4, is a series also. So whatever is going through R34 is also going through R3 and also going through R4. And those are in series. There's no split. All of the current goes into the set, splits, and comes back together, and goes through those. That's the junction rule. Whatever current goes in is the same as the current going out. So I know the current through 3, and I know the current through 4. I3 is equal to 0.927, and R4 has I4 of 0.927 amps. You know the rules, we just are applying the rules. Nothing unusual there. If I know the current through R3, and I know the current through R4, what else do I know? I know the voltage across I3 and I4. I know V3 equals I3 times R3, and I know V4 equals I4 R4. What are those voltages?
3.708.
Say it one more time.
3.708 and 2.72.
3.71 volts and then
781.
Did I get those right? Okay. Now this is where it gets a little bit tricky, but not much, but a little bit. I know there's a 9 volt total drop, and I know 3.7 of it happens here, and I know 2.7, 2.8 of it happens here, which leaves a certain amount left to drop across this one and that one. Which one has more drop? I don't know. I don't know from that top drawing. I can't figure it out from that top drawing. So I got to go to my second drawing. Bless you. I know the current through this equivalent, and I know the resistance of that equivalent. So I can find the voltage drop across 1 and 2. V equals I times R. So V12 equals I1 times R12. I out of the battery, this one. I know how much current is going into resistor 1, 2, which is this set. And I know the resistance of that set. If I know the resistance and I know the current, I can find the voltage. Once I have the voltage, I'll know the voltage across both because it's a parallel set. That's the rule. We just keep using the tools that we have to get more information. The more information we have, the better. Whew. Okay. What is that? I is 0.927, R is 1.2. What is the voltage drop? V12, you got to say it louder, I'm sorry. 1.11 volts. There's a 1.11 voltage drop from here to there. Makes no difference what path you take. From this side to that side, that's how much you drop. So that means V1 is 1.11 volts and V2 is 1.11 volts. Look at your rules for parallel resistors. You know that's true. Whatever the voltage drop across the parallel set is equal to the voltage drop across each one. V12 equals V1 equals V2. Now I know the resistance, I know the voltages, I can find the currents. How do you find the current? V equals IR. I is V divided by R. I know V, I know R. I can find the currents. I1 equals V1 over R1. 1.11 divided by 3, it's going to be in the vicinity of a third. 0.37 amps. And I2, I have V2 divided by R2. It's going to be just a little bit more than a half. 0.55. If I add those two things together, I should get 0.927 by my other rules. Okay. Now, what do I know? I know the voltage drop across this set. I know the voltage drop across this one. I know the voltage drop across that one. And I know the total voltage drop. So I have two options. Both are equally valid and both will give me the same answer. I could take 9 minus 1.11 minus 3.71 minus 2.78, and whatever is left will be the voltage drop across these two. Or, I mean, that's great. If you do that and you get the voltage drop, sweet, you're done. You can get the voltage and then the currents, life is good. Or equivalently good, equivalently valid, and equivalently useful, I could find, I know the current through this. It's going to be the same as here. I know the current through that one. I know the resistance of that one. I can find the voltage drop across that one. V across 5, 6 equals I times R 5, 6. And then I'll know the voltage drop across the set, which means I'll know the voltage drop across each one, which means I can find the current across them, current through them. Both of them should give you the same voltage. I don't care which one you do, but somebody tell me what the voltage is. Say it one more time.
1.39.
39? Which way did you find that? So you put 0.927 times 1.5? Looks good to me. No, looks good to me. I was just checking it, but it looks good. You're multiplying by a little less than 1, so it should be a little less than 1.5, and it is. That's also going to be V6. You can find the current the same way we just did. V equals IR. I is V divided by R, so I through 5 is going to be V5 divided by R5. A little bit less than a third, so 0.2 something. What is it?
0.23.
Now, we know how much current is coming into this, and we know how much is going through the top part. You could just take the current here, 0.927 minus this, and that would give you current through 6. Or you could do V6 divided by R6. Both will give you the same answer. What is I6? Looks about right to me. That's it. That's the whole thing. That was the hardest one you've ever done before in your whole life.
For like resistors 1 and 2, when you add up the amps, it's not 0.927.
It should be close. We rounded off at every step, so it's not gonna be exact, but it'll be close enough. It'll be close enough that you can check your work.
Oh, wait, never mind. It's 0.93. I don't know what.
Slightly different, but that's just because of rounding issues.
1.93, that's all.
All right, I'm going to give you 2 last rules. We didn't get quite as far as I'd hoped, but it was good practice. I think it was definitely worth doing.
When you look like over these, if you could post like a few of them, like on Blackboard.
Probably. You want me to just take pictures of them and post them?
Yeah.
Okay. I think I can probably do that. All right, so I do want to give you Kirchhoff's rules because it's more tools at your disposal. You already know them, but I'm going to make them formal. Kirchhoff's rules. There are 2 of them. 1, the loop rule. The loop rule has to do with voltages. When you have complex circuits that have multiple batteries in them, sometimes Ohm's law isn't enough. For these, for the ones we've been doing, Ohm's law is enough. That's all you really need to solve them. There's only one battery, there's only one direction the current could be flowing. But sometimes it's too complex to know which direction the current's going to be going. If there's more than one battery, or if there's a lot of splits that have various strange angles, you just can't solve it with just Ohm's law alone. You need more tools. Sometimes you just hit a nail and all you have is a wrench. And like you could try to force it, but it's not the best way to do the job. This is another tool in your toolbox. The loop rule, also known as the voltage rule, says that, I'm going to say it multiple times, so don't ask me. I'm going to say it numerous times. It says that around any closed loop in a circuit, the change in voltage will equal 0. I'll say it again. The total change in voltage across any closed loop in a circuit will equal 0. If you go through any closed loop in the circuit, any closed loop, you start at one spot, you end up at that spot again, the change in voltage will equal 0. If I start here and I go around this circuit, There's lots of different paths I can take to get back to this spot. Regardless of what path I take to get back to that spot, the total change in voltage is going to be 0. I go this way, I cross this resistor, I have a drop in voltage, minus 1.11. I cross this, I get a minus 3.71. I go across this, I get a minus 2.78. I go, say, the bottom branch, I get a minus 1.39. I go from the negative terminal to the positive terminal of the battery, I'm going to go up in voltage because I'm increasing my voltage by 9 volts. I get back to where I started. I haven't really changed anything. I'm back to where I started. My change in voltage equals 0. From that, I can derive equations. We're going to do several examples of this in class next time. The last one that I'm going to talk to you about today, and then you're free to go. Number 2, the junction rule.
What's a junction?
A conjunction junction? It has to do with currents. A junction is a split in the wire. You know that. Somebody said it already. They already answered it. The junction rule says that whatever current goes into a junction will equal the current going out of the junction. Remember, parallel sets were defined by having a junction in them. Here's a junction right here. It's a split. Whatever current is coming in, this is I out of the battery, it's right here, is going to equal the current going out, I2 and I1. Whatever comes in equals what's going out. Again, you can derive equations that helps you solve stuff using that rule. We will solve problems, very complex ones, next class. Before you leave, hand me your sample circuits. Leave them on the desk right here by this multimeter. Have a great day. I'll see you guys next time.